This meeting.
So in our previous class, we discussed about dynamic routing. We have taken routing information protocol RIP, and we have seen how does the RIP elect the best path with the help of hop count. So whichever has the better path with less number of hops, that path will be preferred. And we also have seen different versions of RIP version 1 and RIP version 2. We have seen RIP version 1 is classful with no subnet information being sent to the neighbors, whereas RIP version 2 is classless, where it sends the subnet information to the neighbor. That way, it will elect the best path based on the longest prefix match. Any questions from our previous class, guys? Any questions, guys?
No, sir.
Okay, all right. Let's start talking about OSPF, guys. OSPF is another dynamic routing protocol. We'll talk about why OSPF, what are the advantages of OSPF, and we'll also talk about OSPF configuration and also OSPF neighborships and all. Okay, let me start sharing my screen. Okay. OSPF is open shortest path first. So OSPF is a link state protocol, guys. What is link state means? It will just calculate the best path based on what is the lowest cost to reach the neighbor. So if you observe EIGRP, it is, if you observe RIP, it's a distance vector protocol. So what does that mean is, let's say you have this is the source, or let's say there is another source here, and the source path is this way, this way, this way, this way, and then this destination. And there is a different path via this way, and then this way, and then this way, and then this way, and this way, and then this way. So the reason why RIP is a distance vector is because whatever the information that it goes from here to here will be passed to this router, this will be passed to this router, this will be passed to this router. So this router will think, if I wanted to go to this destination, I have to go to 1 hop, 2 hop, 3 hop away. So it will choose the best path by looking at the entire path. Right, so here also this router will pass information like, if I want to go to the street, it's 1 hop away. So this will add to this router. So this will take 2 hops away, 3 hops away, 4 hops away, 5 hops away, 6 hops away, like that. So this also will check the entire path to reach the destination. So if it will check the entire this path, it will check the entire this path, and whichever is the smallest path, that path will be used as the best path. That is a distance vector protocol. It will calculate the best path by looking at the entire flow of the connection, entire flow of the path. Whereas the OSPF, it does not work like that way. So how does the OSPF work? Let's look at that. So here, if we are running OSPF in this path, this will not look at the entire path, and this will also not look at the entire path. It will check what is the cost from this router to reach this router. If the cost is 100 here, and if the cost from here to going here is 50, it doesn't care how many hops next this router is going through or what is the cost after that to reach the destination. It will just see what is the lowest cost from me to my neighbor. That is why it's called as a link state protocol. It will just look at the link cost, and if that link cost is lower, that path will be preferred. And what is this cost? Cost is calculated by the formula cost equal to 10 to the power 8 divided by link bandwidth. Okay, so let's say this is a 1 gig link, 1 gigabit per second link, and let's say this is 100 megabit meg link. Okay, so this can send the data up to like 1 gig packets per second. This one will send up to like 100 meg per second, right? So the calculation of the first one is cost equal to 10 to the power 8 divided by 1 gig link is equal to 10 to the power 7. Okay, that will make it as cost as 10. For 100 meg, or let's say 100 meg is also same as the gig, right? So I wanted to make the correction. Let's say 10 meg. Okay, 10 meg link. Okay, so 10 meg link is equal to cost is equal to 10 to the power 8 divided by 10 to the power. That will make it as 100. Okay, so to select the best path, this is the cost as 10, and this is the cost as 10, and this is cost as the 100. So obviously we use the lower cost link, right? So because lower the cost, higher the preference. So whichever cost has the lowest cost, that path will be preferred, and that cost is calculated with the help of this formula based on the link bandwidth. Whatever the bandwidth that we are getting, based on that, you will get the connection cost. So whichever has the lower cost, that path will be preferred to send the packet out. Any questions on the cost calculation, guys?
So what if both the costs are same?
Equal cost multipath, ECMP, load sharing between both the routers. We have seen this. We have talked about if both the metrics are same, what is the condition in the routing table will happen, guys?
We'll choose random. It's a decision.
I'm sorry.
Sharing load.
Yeah. If the metric is matching on both sides, that means if the cost is matching on both sides, it is sharing the load between both the links. Any other questions?
Okay.
Okay, now let's see how does the OSPF uses the neighborship. How does it forms the neighborship between the two devices, right? So let's say there is a router here and there is a router here. This is called R1. And let's say this is R2. And we wanted to form a neighborship between R1 and R2. We wanted to form OSPF neighborship. Okay, between R1 and R2, we wanted to form the OSPF neighborship so that they can exchange the information between the devices. Okay, so now how does these neighbors form? So meaning there is a step-by-step process on how does the neighbors form in terms of having the relation. So first step, first stage is called down state. So in the down state, both of the routers are not sending any hellos. Okay. That is the first stage. Both the routers are not sending any hellos. And the second stage, so this router will send a hello message to a group called 224.0.0.5, which is a multicast group. So this one will send a multicast message to this group. And this one also send the multicast message to that group. So both of them will be listening on the same multicast group, so the hellos will be exchanged. Okay, so in the second stage, this is called init state. A router will send a hello message to the multicast group. That is the init state. And then the two-way state. Both hellos will be exchanged between both neighbors. So this one sent a hello message. This one sent a hello message. This one sent a hello message. This hello message is received by this router. This hello message is received by this router. That completes the two-way state. Okay. And next comes the start state. So start state is where, let's say this router has the information of some 10 networks. Right? Let's say the information of 10 networks. Let's say this router also has like 20 network informations. Okay. This one will start sending this networks information to this router. This one will start sending the information to this router. Right. So the whole purpose of making two routers communicate is making them. I mean, the whole purpose of making OSPF neighbors is to communicate between the networks, right? I mean, to make it simple, let's say you have a building A and you have a building B. You have a router here and you have a router here, and you have some PCs, and that will be connected to the switch, right? Switch will be connected to the router. Similarly, in this building, you have a switch, and then you have other PCs connected here, and you will make a OSPF relationship between these two routers, right? So now, once the OSPF neighborship is peering, this router A for the building A should send all of this information to the building B router. Similarly, building B router should send all of the information to the building A router, right? So that is where the exchange will be started to happen. So in extract state, in state database will be sent to its neighbor. Okay. Exchange database from neighbor is received. On both ends. So this router will try to send its database information to this router. This router will try to send its database information to this router, and they both will receive the other end in the exchange state. Okay. Loading state. It will make sure it is not missing any information and ask for validation. So let's say R1 sends some information to the R2 that it got 10 networks, and R2 will send information to the R1 that it got 20 networks. So they will double check, make sure they're not missing anything. Is R1 will ask R2, do you have 20 networks? Is that correct? R2 will ask R1, do you have 10 networks? Is that correct? So they'll cross check and validate in the loading state. And finally, the full state. Both routers are synchronized. Database, and they are fully formed OSPF neighbors. Okay. So OSPF works on the multicast. The first hello message will be sent on a multicast group called 224.0.0.5. So that is the initial state, and two-way state is where the hello message will be received on both sides. Extract is where it tries to send the routing information or the database information to the neighbor. Exchange state is where the neighbor received it and it also acknowledges it. And then loading state is where they'll make sure that the information is correct and it's not missing anything from the neighbor. And the full state is where both the neighbors are in the fully synchronized state. Okay. That is how the OSPF neighborship will be formed. Any questions, guys? Any questions, guys?
No, sir.
No, sir.
Okay, so now let's see what is an area in the OSPF. Let's say you have These are all the routers with the OSPF peerings. Let's say these are all having a lot of information on the each router. So every router has its own building. Okay. So now let's say this router has some information. Okay. This router has some information. And if this router has some information, so that information has to be sent to this router. That information has to be sent to this router from here to here, here to here, and here to here, and here to here, here to here. And if something changed in this router, the same information has to be passed all the way to this router and then from all the way here to here. So it is not feasible to update all the information to all the routers inside the same company. So that's why if your company is too big, there is a concept called areas. So what is the concept of areas? They will elect a border router which is connecting both the areas. So in this case, let's make this as one area. Let's make this as another area. So there are two areas here. Okay. So let me make it a little more simple. Let me do one thing. Let's take a big router. Okay. So this is the okay. I just put it as a big router here because I did areas very long, right? So this is area 0. This is area 1. So we have two areas, area 0 and area 1, and this router which is connecting both the areas are called area border router. So area border router is connecting both the areas. Now what does this do is, we are electing a router which is acting as the area border router. So if let's say this has some information, and this information has to be sent to all the routers inside the same area. Okay. And that information will be shared to this border router. But that doesn't mean that information should be shared to all the routers inside this area. So to put it as a common terminology, let's say this person, let's say these are all persons. Okay. Let's say this person know about 1,000 people in the community. So we will send that information to all the routers, all the other persons inside the same group. Okay. But this group doesn't know what this person know. But if this person in this group wants to talk to this person in this group, it will point to this router. So this router is acting as a middleman between this group and this group. So if any person in this group wants to talk to any other person, it will just point to this router only, this person in the middle only. They will not directly talk to the other group person. They will point back to the router. So this way we can avoid sending the updates from every person to every person in the company. We can elect one as the group leader, which can be managing both the groups, which is nothing but the area border router. This will avoid the number of routes being shared in the company. That way we can reduce the lot of updates, and we can put summarization in wherever place. So the router which is connecting both the areas is called area border router, and OSPF works in areas when you have a big network, you are separating them into smaller areas and you are reducing the number of updates. Any questions on areas? Is that clear, guys?
Yes.
Okay, now let's talk about the different types of OSPF tables that each router will maintain. So let's say this is R1, this is R2, this is R3, this is R4. This is OSPF between R1 and R2. This is OSPF between R1 and R3. OSPF between R1 and R4. Okay, so R1 is the neighbor of R2 and R3 and R4. So in the neighbor table of OSPF R1, you will see the neighbors R2, R3, and R4 as its neighbors. In database table, it will see what are the best paths to reach the destination. You have a path 1, path 2, path 3. Let's say the metric here is 50, the metric here is 100, and the metric here is 150. So you will see the database table with all the available paths, with the 50 path, 100 path, and 150 path. So it will show all the paths that are available in the database table. All the routes are available in the database table. And the routing table, which will have the best path. The best path will be 50. So the best path will be only introduced in the routing table, which is the 50th path, which is via R2. So the best path will be in the routing table. So again, neighbor table will have all the neighbor IPs that are OSPF neighbors. Database table will have all the paths to reach the destination. Routing table will have the best path to reach the destination, which is with the metric value of 50. That is stored in the routing table. Those are the different types of tables stored in the OSPF. Any questions, guys?
No.
No, sir.
Now let's talk about OSPF packet types. So R1 has a neighborship between R2 with the between R1 and R2. R1 has 10 networks in it and R2 has 20 networks in it. Okay. So now R1 should send the 10 network data to R2. And that will be sent with a packet called LSA, which is called link state advertisement. So whatever the data that R1 has in terms of routes, in terms of the networks that is sent to R2 via LSA. Link state advertisements are nothing but data messages that are sent between the neighbors to share the networks that they own. To exchange the routes between them, the LSAs are used. So once the networks are exchanged, to validate whether it needs any furthermore information, R1 will send a LSR, which is the link state request. So R1 will ask R2, hey, I got 20 networks from you. Do we have anything else that I need to update on my database? R2 will say no, right? So that is the link state request that R1 is asking about R2. Let's say R2, 20 networks are increased to 21. Let's say someone added a new network beside R2. So now the R2 got an update to send back to the R1 that it had one more new network added, that is done with the link state update. Link state update is like, let's say the database got updated on R2, that update will be sent back to the R1 that it got updated on the database. So it will send the LSU packet that it got updated in the database. So R1 should also update its database received from the R2. So LSA is the database exchange messages. LSR is the request to see if there is any change in the database. LSU is the update to the already existing database to the neighbor that it got some change. So it got some change and it has to update to the neighbor about that change. Okay. Any questions on the LSA, LSR, and LSU?
Sir, for the link state update, the R2 will send to R1 or R1 will send to R2?
If R2 got the database change, R2 will update that change to the R1. If R1 got change on its side, that will send that information to R2. It will be both ways.
Okay, two-way.
Yeah. Any questions?
No, sir.
Okay, let's do a lab with OSPF neighborship and making an connectivity between the two buildings. Yeah, someone brought a good question. What are the parameters to match to become the neighbors? Let me explain. Okay. Okay, so what are the parameters that are need to be matched to become the neighbor? Let's say there is a R1 and there is R2. And we talked about making these two neighbors between them, right? So what is the parameters to make sure they are matching in the, they are becoming the neighbors? The first thing is reachability. R1 should be able to reach R2. They both should be able to communicate. For that, they need to be on the same network. Same network. Otherwise, there is no reachability, right? R1, R2 should, if they want to become the neighbor, they should be reachable and they should be in the same network. Second one is, they both should have same
Subnet.
yeah, subnet is one thing. Subnet and same network is same thing, right? Same network or same subnet. Yeah, you can put same network. You can say they both should have same password. If you are protecting a password on your interface, they both should have the same password. If R1 want to become the R2 neighbor, on the link you can put a password, and R2 should have the same password. So password should match. Another important thing is they both should be in the same area. We talked about areas, right? So when we are grouping them, they both should be in the same area. So if R1 wants to become the neighbor with the R2 or R2 wants to become the neighbor with R1, they both should be having the same area ID. Otherwise, they will not be neighbors and they will not exchange information. Next. They both should have same packet size. Okay, which is called MTU. So if R1 is sending some data to R2, the R2 should be able to understand the packet size. Otherwise, the packet will be chunked into multiple packets and R2 will not be able to understand. So this interface MTU, maximum transmit unit, and this interface MTU should be same. Otherwise, let's say I'm sending the information of this packet size, and if it is chunked between two packets, R2 will not be able to understand the hello message correctly. So the packet size should be same on both sides. And they both should have same network type. Meaning broadcast, multicast, unicast, point to point, right? So they both should have the same network type. Right? If R1 is using the network type point to point, it will be unicast. Or usually, if you don't specify anything, it's a multicast group, as I mentioned, 224.0.0.5. So, okay, multicast or unicast. So they both should have the same network type. So these are the basic conditions for the R1 and R2 to become the neighbors between both of them. Any questions?
No.
Okay, thank you, Sirisha, for that question.
Sir, what is this process called? Do you have any
OSPF neighborship process.
I'm sorry, sir.
OSPF neighborship process.
Neighborship.
Okay, let's do the lab. Let's take it. Okay, I think we have 15 minutes. That's enough. Okay, I'm going to share my screen. So I'm taking a small network. It's just like a router on a stick. I'm gonna put one network here. So I'm gonna take a couple of pieces here, couple of pieces here. Okay. So for our ease of understanding, I'm gonna put some notes here. I'm gonna pick this as building A. I'm gonna put this as building B. So I'm gonna take this as a 10 network, 10.0.0.0/24 network. I'm gonna pick this IP as 10.0.0.10. I'm gonna pick this IP as 10.0.0.11. I'm gonna create a gateway here, which is 10.0.0.1. I'm gonna put this as VLAN 10. Similarly, this is building B, VLAN 20. The IP address is here is 20.0.0.10. The IP address here is 20.0.0.11. I'm going to pick 20.0.0.1 as the gateway of this one. So for the connectivity spice, just a basic connectivity. Access ports, trunk port allowance to that one. Similarly, access ports. And then a trunk port. Now let's have a link between these two routers. And this is nothing but the OSPF neighborship link, right? So OSPF neighborship link on, let's pick 30 network, 30.0.0.0/30 and pick /30 here. We can make this as 30.0.0.1. You can pick this one as 30.0.0.2. Okay, so now the goal is the building A should be able to talk to building B. They're in two different buildings. We need to make a dynamic relationship between these two routers and then make this network communicate with this network. That is the end goal. Any questions on this topology or what we are trying to do?
Sir, on what basis we choose switches and routers? Like we have different switches and different routers, right?
It depends on the capacity. I mean, it's like you're trying to buy an iPhone. On what basis you wanted to buy an iPhone? Do you want to go with iPhone 10, iPhone 11, iPhone 12? It depends on what kind of features that you want. You want like more camera features? Do you want like high CPU? Depends on the model features, right? Similarly, every switch has its own features. Here in this lab, we are just putting some basic switches and routers. Is that clear?
Yes, sir.
Yeah, every switch will have its number of ports, like number of ports that it can handle. Every switch will have number of CPUs, how much fabric it can switch between the devices. So there is a limitation on the switch, right? So number of ports will be there, how it is getting managed in terms of getting a speed, memory, all of that will be in the consideration.
So what is the difference like with the normal switch and the multi-layered switch? Like what is the maximum
Multi-layer
pieces
switch
it gets
is like
connected
it
with?
supports routing, right? Multi-layer switch will support the routing. Normal switch will not support routing. It's plain layer 2 with the VLAN, but it cannot attach IP addresses on the layer 2 switch. A multi-layer switch you can apply the layer 3 gateway. You don't need a router here in this lab. You can just put a multi-layer switch because it can be capable of creating gateways. But on a normal switch, you cannot create a gateway because it does not know what is an IP address. It works on the MAC addresses. Clear?
Yes, sir.
Okay. I'm going to go to PC0, give the IP address. Subnet mask is 255.255.255.0. This one. .0.0.1. 1.0.0.1, which is the default gateway. We're going to go here, create a VLAN 10 and assign these ports on the VLAN 10. Enable mode, config terminal, VLAN space VLAN 10. Name is building A. Exit. So we created a VLAN. Now we can assign the ports. /1, 0/2. Interface FA 0/1. Switch port mode access. Switch port access VLAN 10. Interface FA 0/2. Switch port mode access. Switch port access VLAN 10. That is done. So this part is done. This part is done. Now let's look at this part. This is FA 0/3. So now interface FA 0/3. Switch port mode trunk. Switch port trunk allowed. VLAN 10. So to check the VLAN information, show VLAN space ID space 10. So these two ports are in VLAN 10 now. So now let's go here and then create an interface VLAN sub interface for this gateway. So I'm going to go here. CLI. Go here and then do interface gig 0/0/0 node shut. Thanks. Interface gig 0/0/0.10 for the VLAN 10. I created a subinterface of .10. Just like your router stick configuration, you will do encapsulation .1q with the 10 tag where you can receive the VLAN 10. And then you can define the IP address as 10.0.0.1, which is the gateway, and then define the subnet. And then do no check. To check the IP address, you can do show IP interface brief. It's 10.0.0.1. It's up and up. Protocol and the status are up. Now let's try to see if we can ping the gateway from here. So go to desktop and prompt, and then do ping 10.0.0.1. Okay. So from here, I was able to ping the gateway. So now let's go here and then try to ping the gateway. And prompt ping 10.0.0.1. Okay, so this PC is able to ping the router and this PC is able to ping the router. Now, let's make an OSPF relationship between these two by creating these interfaces. Okay, so let's see 30.interface gig 0/0/1 gig 0/0/1 IP address 30.0.0.1 255.255.255.252. Oh shit. Okay. Similarly, let's go here and then define 30.0.0.2. .0.0.2 255.255.255.252. Notion. Let's see if we are able to ping from here to here with the same subnet, because one of the conditions to become the neighbor is they have to be in the same subnet and they should be able to ping. Okay, now I was able to ping between both of them. So we know the connectivity is between here and here is good. So now let's create the OSPF router OSPF one. It can be any number. The process ID can be any number. I'm just creating a process ID as one. Here I can put the network statement. I can do network. I am owning 10 network in this building, so I'm going to put 10.0.0.0, and then I can put the subnet, which is subnet opposite is the wildcard, right? So I can put the wildcard 0.0.0.255, and then I'm going to put it in the area 0. Okay. If you don't know what is a wildcard, we will discuss maybe when we talk about IP address calculation in our class. But think that wildcard is the opposite of the subnet. If your subnet is 255.255.255.0, the wildcard will be 0.0.0.255. It's opposite to the subnet. Okay, so for now, let's keep it that way. And then I'm also owning network 30.0.0.0. It's 0.0.0.0.3 area 0. Okay. Here also similarly, I have to create an OSPF router OSPF 1, and then define network. Here I am owning 20.network, so 20.0.0.0.0.0.255, and then area 0. Also, it's part of 30 network 30.0.0.0.0.0.3 areas. Now to check the OSPF neighborship, you have to do show IP OSPF neighbor. Okay. Now it's in the two-way state, it's still exchanging the information, so let's wait. Two-way is where it exchanges the hellos. Remember, we were doing the stages. We talked about initial state, two-way state, start state, exchange state. So it's trying to exchange the neighbors. Yep. Now it went to the full state. Okay, so now it is in the last state where both of them are in the neighborship between the neighbors. So now I have the connectivity between this router and this router. Also, let's complete the connectivity between the 20 network here. So I'm going to go here. Config. Okay, I'm gonna go create a VLAN 20 and assign the ports in the VLAN 20. Okay. Enable config terminal VLAN 20, name building B, interface FA0/1, switch port mode access, switch port access VLAN 20. Similarly, interface FA0/2, switch port mode access, switch port access VLAN 20. So this part is done and this part is done. Now let's create this one, this link. Interface FA0/3, switch port mode trunk, switch port trunk allowed VLAN 20. So this part is done. Now let's go to router and then create a sub interface. Config terminal, interface geek 0/0/0, now shut. And then create a sub interface, interface geek 0/0/0.20, encapsulation .1Q20. IP address has 20.0.0.1, 255.255.255.0 as the gateway, and then do no shutdown. That should complete this PC pinging to the desktop. I mean the gateway. Let's check that. Let's wait for this thing to come up. Now let's try to ping. Pinging 20.0.0.1. It's pinging. So now from here, PC0, let's try to ping the PC2 here. In this PC0, in this building A is trying to talk to PC2. Let's do the simulation. Let's start, and then go to PC0, and then ping 20.0.0.10. And let's move it here. The packet came to the switch, which is sending to the router. Router should check its routing table, should send it back to the 30 network because that's where the network segment is there. The router should send that to the sub interface with that VLAN tag with the 20. It's broadcasted to both the PCs. This one discarded it. This one should be replying back. This one is replying back. This got to the switch. Then go to the router. The router should send it back to the router. The switch, and this switch should reply back to the PC0. So now you got the reply back that it was able to communicate to the other building PC. Okay. So to keep what we should look, so here we have to check the ARP-A. So this PC knows the ARP entry of the gateway. We can check the MAC address table, show MAC address table. This switch knows the MAC address entries of the VLAN 10. And here you can check the ARP table, show IPR. The ARP table will give the information of the 10 network because this ARP lives on this router. This is the gateway. And here, if you see, it will see the 20-dot network. So IPR, you'll see the 20-dot network learning on that one. And if you want to check the OSPF neighbor, you can do show IP OSPF neighbor, which is full state. And if you want to check the database, you can check show IP OSPF database. Database will have all the routes that are learned via OSPF. And if you want to check the best route, you can do show IP route just to check the routing table. That will be the best route. It is learned via OSPF. O means OSPF. O means OSPF. Okay. All right. I'm going to stop there, pause there. Any questions from this lab? I want you guys to do the lab with your hands by following the lab what I did. That way you get more clarity. By looking at what I do will not give you all the information, but when you are doing that will get more information for your brain. So I want you to go through the recording, make sure you do it. Okay. Any questions, guys, before I let you guys go?